Hello everyone, my name is Fighting Pepper and welcome to part 2 of how to code 3D Perlin noise terrain generation in Scratch. In the previous part, we learned the algorithms of Perlin noise and coded them up in Scratch. This episode, we're going to be rendering that terrain that we generated in 3D, so we can look and move around it. How we'll do this is render a whole bunch of points on the surface of the terrain, and then we will project those points onto a 2D screen in the form of circles. And we'll store each of those points in a grid. Now we're going to use Turbo Warp for this because this runs pretty slowly in normal Scratch. So you're going to need to take your Perlin noise project and save it to your computer. So now we get a file here. Now in Turbo Warp we can go to File, Load from your computer, and choose the file we just exported. First of all, let's go to when the flag is clicked, remove the Draw World block from here. Then we can actually just delete this whole block. Again, make sure you've saved this to your computer so you can go back to your old project if you ever want to. Now we're going to be redrawing our terrain every frame, and having to use the find point height block for every single point we want to render every single frame is going to take way too long. So rather than doing that, I'm going to create a list called heights. And again, I'm going to make all my lists and variables for this sprite only, but it doesn't really matter. Then I'll make a custom block called create heightmap. Run without screen refresh. And this block is going to essentially do what our draw world block did, except without the drawing it. Rather than drawing it, it's going to store each of the positions in a list. Like the gradient x and gradient y lists, this list is going to be a grid list, and it's going to store a grid of heights, which represents our world. It's going to hold all the items in a row, and then all the items in the next row, then all the items in the row after that, etc. Now we created the grid size variable to hold the size of our gradient x and gradient y lists. Now we also need the variable to hold the width and height of our height map. I'm actually going to rename our grid size variable to lattice count, because this is the amount of lattice points in a single row on our grid. And I'm going to make a new variable called grid size, which will hold the size of our height map. For each row in our height map, we would probably want multiple points in between each of the lattice points of the grid. Remember, each of the lattice points have a height of 0, so if we only included those in our height map, we would have a very boring height map. So I'm going to make another variable called detail, and this variable will hold how many points between each of our lattice points we'll have in our height map. I'm going to set detail to 30 when the flag is clicked. Then I'll set grid size based on the lattice count and detail variables. I'm going to set it to lattice count, and then we're going to subtract 1 from lattice count, remember, just like we did in Draw World, because the lattice points are sort of at the corners of each of our cells. So in each row we have 1 fewer cells than we do lattice points. So lattice count minus 1 times detail. That's what we set grid size to. Then I'll put our create height map block right after we make gradients. Now in this block we'll start by deleting all of our height map, delete all of heights. Then we'll do something similar to what we did in Draw World. Start by setting y to 0, then repeating by grid size. So this loop is looping through our rows. Then in our rows, then we're going to set x to 0, and again repeat grid size, so traveling down each of the points in that row. Each time we're changing x by 1 divided by detail, and change y by that same amount, 1 divided by detail. So say our detail variable is 30, which it is. After 30 iterations of this loop, the x will have changed by 1, and by grid size iterations of the loop, x will have changed by 1 minus lattice count. And then inside the inner loop for each point, we'll find point height, and then add our height variable to our heights list. So let's show our heights list and run the project. If your lattice count and detail is the same as mine, your list should be the same length. Alright, now it's time to make the block which will actually draw our terrain. Now call it draw terrain. Run without screen refresh, and I'll stick it at the end of when flag clicked. Keep in mind that I'm going to use our y-axis in this 3D space to represent the axis which determines the height. So a hill would have a higher y value than a valley. And then I'm going to use the z value for what we have been using the y value for. The reason I'm doing this is because the z traditionally represents how far away an object is from the camera. Speaking of the camera is the point at which we are viewing the world from. So I'm going to make a variable z and this will hold the Z value we're at when we're drawing the terrain. I'll start by setting Z to grid size. So we have a grid size by grid size grid of heights, and we're starting at the far end of it. So we start at the back and then we draw towards our camera so that everything is layered correctly. We're also going to erase all at the top because we're going to be using our pen to draw things. Now we repeat by grid size, changing Z by -1. So by the end of the loop, Z will be 0. So we've covered all of our rows. Then inside this loop, we're going to do the same with the X. Set X to grid size, then change X by -1. And yeah, repeat by grid size. So this will cover all of our points. Now for each of those points, we need to get their height. So I'll set height, and recall from part 1 the formula for getting something from a grid. That is item, and then we multiply the Z or Y value by the grid size, and then to that we add our X value, and then we add to that one more because lists in Scratch start with 1. So I explained this briefly last episode, and then this is going to be of the heights list. That's what we're setting height to. So if you remember how we created our height map, we stored the positions like so, each of the positions in a row, and then each of the positions in the next row, and so on. So every time we change X by 1, that's moving down 1 in the row, we're changing our index by 1. And every time we're changing Z, that means we're moving to the next row, we're changing our index by grid size, because we have to move all the way to the end of the row and then back around through the next row until we're above where we were before. Now that we've got our height, we can position ourselves. I'll create a new block for this called draw point, then 3 inputs, an X, a Y, and a Z. Run with that screen refresh. Now for this, we need to take our coordinate in 3D space and then project it onto a 2D plane, which is the screen. Now let's think about this. What happens when we change an object in each of the different axes? Well, if we change an object in the X-axis, then the only thing that changes is the X position on the screen. Similarly, if we change an object in the Y-axis. So clearly, the position on the screen is directly proportional to the X and Y position of that object. Now let's take a look at the Z-axis. That's how far away something is from our camera. When the object gets closer to our camera, it appears bigger. So this makes us think that when an object is closer to the screen, the X and Y position of that object has a greater effect on the X and Y position of that object on our screen. What I mean by this is that if an object is very far away, moving it to the left and right is not going to affect its position on the screen very much. But when that object is quite a bit closer to our camera, moving it left and right is going to have a larger effect. That makes us think of the following formula. Go to X divided by Z, Y divided by Z. So moving an object left and right will change its X position on the screen, moving it up and down will change its Y position, and then moving it forward and backwards will change how much of an effect the X and Y positions have on that object's projection onto the screen. Now there's one last piece of this equation. We need to multiply each of these values by a constant so they aren't too small. This constant is called the focal length. So I'll make a variable called focal length. When our flag is clicked, I'll set focal length to 300. Back to our draw point block, we're going to multiply each of these values by focal length. You can see here that changing focal length is very similar to changing Z. When our focal length is larger, objects appear larger. Another way to think of this, decreasing the focal length is similar to increasing the FOV. Alright, but enough talk about this formula, let's get to the exciting part. Pen down, pen up. So we just draw a dot. You can set our pen color to something if you want. Let's set it to a nice green color. Then we use this block when we draw terrain. Then our inputs are X for the first one, Z for the third one, then the middle one will be our height variable. Now remember that our height value ranges between -1 and 1, so this is not going to have much of an effect. So let's multiply it by something to make it bigger. How about we multiply it by detail? This makes sense because detail affects how large our grid is. So if we have a larger world, it would make sense that we'd want the height to have more of an effect. So the proportion of height to world size remains constant. Let's try this out and see what happens. press the flag, and then you'll see here patterns of terrain are being drawn. Alright, there's a few things you'll note. One is that the terrain is off to the side, and the other is that the terrain is being drawn in very small pixels. Well, both of these issues can be fixed. Right now, let's celebrate that we have in fact drawn 3D terrain. Doesn't look like much now, but once we get to moving around, it will be a bit more obvious that this is in fact 3 dimensions. Now let's get to moving around. Remember I was talking about our camera, how the camera position is the position that we're viewing the world from? Well, let's make variables to hold that position. I'll call them camera X, camera Y, and camera Z. Let's set all these variables to 0 when our flag is clicked, like so. I'll show these variables and convert them to sliders. Right-click and select slider. That way we can move around our camera. Now we need to code these variables into our rendering scripts. How we're going to do this is move the terrain around based on our camera position variables. That way we can just use our simple projection formula to get it onto the screen. This process of shifting a world around is called transformations. Let's think about how a transformation for camera position would work. Well, when our camera moves to the right, then our world appears to move to the left. And when our camera moves upward, our world appears to move downward. So maybe we simply subtract our camera variables from our position variables. We'll do that in draw point. For each of our inputs, subtract camera X, camera Y, and camera Z respectively. And we need to put this draw terrain block into a forever loop, because right now we're only drawing it once. Let's run this now, and try changing our sliders. Let's wait on the camera Z slider, don't mess with that one yet. I'm going to change our camera X, and you can see we are in fact scrolling back and forth. Then I'll change our camera Y, and yeah, there we go. That's looking great. Okay, really quickly, a small visual glitch that we should just fix right now. You see that line in the back and that weird line of terrain that doesn't seem to match any other terrain? Well, that happens when it tries to draw terrain that is off the grid. We're looping too much. So let's set our X and Z to grid size -1 instead, and repeat by grid size -1. And we see those lines are gone. Now let's try changing our camera Z variable. And it seems to work just fine, except, oh, what is that? Our terrain is appearing above us also. That is because that terrain is behind our camera. When that happens, our projection scripts start behaving weirdly. So in draw point, let's just check if Z is greater than 0. So that's just making sure that everything we draw is in front of the camera. We don't draw anything that's behind the camera. This is looking great. But what about rotation? Let's go ahead and add that now. Make variables called camera rot horizontal and camera rot vertical. So those are 2 rotations, an up and down rotation and a left and right rotation. The reason I'm not using X and Y to describe the rotations is because that could get confusing. Because rotation is often defined by the axis that we're rotating around. So our horizontal rotation is traditionally called our Y rotation, which is very counterintuitive because that's left-right. Alright, let's set these guys to 0 when our flag is clicked. Alright, so we need to do more transformations for our rotation. However, these transformations require a little bit of prep work. We're going to use sine and cosine for them. Computing sine and cosine is quite taxing on the computer, and because our camera rotation doesn't change at all mid-frame, we can just compute the sine and cosines once at the beginning of each frame, and then not again the rest of the frame. Let's make 4 variables called sine rot h, that's the sine of horizontal rotation, sine rot v, cos rot h, and cos rot v. I'll make a block to calculate these variables called trig calculations. These are trigonometric functions, so that's why I'm calling this trig calculations. So we'll just set sine rot h to sine camera rot horizontal. Sine rot v is sine of camera rot vertical. Rot h is cos of camera rot horizontal. And cos rot v is cos of camera rot vertical. Then I'll use this block in our forever loop before we draw terrain. Okay, now it's time for our transformations. But if I put our entire transformation formula inside each of these three inputs, then this draw point block here is going to get quite long. Let's instead make variables to hold our transformed positions. I'll call them transf x, transf y, and transf z. Then we're going to need to make sure to set these all at once, not one at a time. So we need to make a block called set transformed positions to x, y, z. Run without screen refresh, and then the code here is very simple. Just set transformed x to x, set transformed y to y, and set transformed z to z. This block might seem kind of pointless, but the important part is that we're setting them all at the same time. I'll explain more in a moment. Let's use our set transformed position blocks here, and I'll move the inputs from draw point into that block. Then we'll use our new variables, transf x, y, and z, as the inputs to draw point. Alright, now let's transform our positions based on our horizontal rotation. And by the way, the following transformation formulas come from the Scratch user Math. They have a great 3D tutorial which I'll link below. So let's do this. Set transformed positions, and then make sure to copy these formulas very carefully, because if you do something wrong, your rendering will get all wonky. So for the first input, it is transformed z times sine rot h plus transformed x times cos rot h. Now this is our horizontal rotation transformation, so we're not worrying about vertical at all. So we can just leave the vertical input as transformed y. Now for our final input, transformed z times cos rot h minus, be very careful to use a minus here, not a plus, transformed x times sine rot h. Now you might be able to see why we had to use our set transformed positions block. In our third input here, we're setting based on transformed x, but this transformed x is the one that we set in the previous block. If we just use these three blocks in a row, then this transformed x here, this input here, that would be what we set it to at the very beginning of the block, which we do not want to happen. That would be as if we would put this into this input with transformed x. So we need to set these all at once, all based on the same previous values of these variables. Let's do a quick test. Show the horizontal rotation variable, make it a slider, and try changing the variable. And you'll see we rotate. So there we go. That's working very good. If yours is not working very good, you should check these formulas over once more. Alright, now let's move to the vertical transformations. For these guys, we don't want to worry about our x, so just use transformed x as the first input. Then again, copy these very carefully. For our y input, we have transformed y times cos rot v minus transformed z times sine rot v. Now for our z input, this is transformed y times sine rot v plus transformed z times cos rot v. Now let's show our vertical rotation. I'll make this a slider from -90 to 90. And now we should be able to look down and up. Awesome! Okay, this is looking great. We now have a working 3D renderer. However, it's really annoying to have to use all of these sliders. So let's make some movement scripts. Make a block called move camera. Run without screen refresh. I'll drop this in our forever loop before we do our trig calculations. Let's start by changing our camera rotation horizontal by key right arrow key pressed minus key left arrow key pressed. Then we're going to multiply this by 4. You might have seen things like this before, but Boolean values return either a 1 or a 0 when put into a number input. So we can use that to our advantage here. 1 if key right arrow pressed, -1 if key left arrow pressed, and 0 if both are pressed or neither are pressed. And actually we need to reverse these. It's going to be the left arrow minus the right arrow, which is kind of weird, but yeah, that's the way things work. Now we change our camera rot vertical by up arrow minus down arrow, also times 4. Let's add some bounds on our vertical rotation. If vertical rotation is greater than 90, we shall set it back to 90. And if it's less than negative 90, we'll set it to negative 90. These bounds are optional, but if you don't have them, then if you move the camera all the way up, then you can see the world upside down, which maybe you want, in which case don't put these bounds in. Now we're going to change our camera X, Y, and Z variables. Let's start with our forward and backward movement. Now this will be moving forward and backwards in the direction that we're facing. I'll change camera X by, and then I'll duplicate this stuff, W key minus S key. I'm using WASDEQ movement. Then we multiply this, and then we're going to use more sine and cosine. This time, sine of camera rot horizontal. And then normally this would be enough, but we have this weird backwards horizontal rotation. We're going to need to multiply this by -1. And then for our camera Z, we do the same thing, but multiply by cos. And this sine and cos here is sort of like what's used by move steps. It's just moving forward. If you remember the unit circle I referenced briefly in the previous part, these formulas just come from that. Now for our side-to-side movement, change camera X by D minus A key, and then around our camera rotation horizontal times -1, we're going to add 90. So 90 degrees to the right of the direction we're facing is in the other axis. So moving along that axis, we're going to move side to side in relation to the direction we're facing. Now we need to change camera Z by the same formula, except we replace sine with cos, just like we did above. Finally, for our camera Y, change camera Y by plain old E key pressed minus Q key pressed. E to go up and Q to go down. We can now hide all of our camera variables and try this out. Now we can use our keyboard to move around our world. This is awesome, but I've been ignoring the elephant in the room for far too long. Our world is made up of tiny little dots, and when we get close to them, we can hardly even make out that they're there. So let's change the size of those dots based on our distance to them. In Draw Point, I'm going to set pen size to 800 divided by Z. So the closer we are to a point, the smaller Z gets, and thus the larger our pen size gets. Let's run this. Now we have a very filled in looking world. Now it's sort of hard to tell the shape of it anymore, because it's all one color. So let's change the color value based on the height. So I'll add a new input to Draw Point, call it height, and pass in the height variable like so in Draw Terrain. Then we can set pen brightness to 50 plus height times 80. And this 50 and 80 are just arbitrary numbers. You can change those around to change the pen brightness at any given point. Let's run this. And now, ta-da! We have some very nice looking terrain. This actually looks awesome. However, you'll notice I'm moving around very carefully. Right now there are no visual glitches. There are actually several that we need to address. The first comes when I turn around. Turn around very slowly. And what is that? We have green circles in our face. That's not pleasant. What's going on? The problem here is that those points should be off screen. But our sprite is not allowed to go off screen because of sprite fencing. Now we are in Turbo Warp, so we could just click this lovely remove fencing button. Let's try that. Now when we turn around, yep, no circles to be seen. What if we want this project to work in Scratch too? Then we won't be able to use this. So I'm going to turn this off. And there's actually a very easy fix to this. We just need to set the size of our sprite to infinite. And then it can go as far off screen as it wants. Now I'm afraid our Scratch cat here is not small enough to get a size of infinite. So we're going to have to delete it. But the corpse of our friend Scratchy has a size of 0 by 0. And what this means is that we can set size to 1 divided by 0. Let's just try clicking this block to see what it gives us. And infinity. So we can set size to that. But now we can turn around. And yep, no pesky circles getting in our way. But remember I said we have several visual issues? Yes, we still have more. Let's try moving over the terrain, and everything looks fine, right? It all looks good. But let's go over to this side, and oh yes, we clearly have visual issues now. What is going on? In fact, if we go around to the other side of our terrain, start moving down, things will begin to look a little weird. You see, the problem is the terrain in the back is being rendered in front of the terrain in the front. So we need to make sure the terrain is rendered in the correct order. We need to figure out a way to fix this. Our first thought might be to put all of our positions in a list and then sort them based on which one has the highest z value. We could do that, but that would take a really long time to do each frame and would make it super laggy, so let's not do that. Instead, we can choose how we loop very carefully. The trick is making sure we always loop toward our camera. Our x and z positions start at far away from the camera. Throughout the loop, they become closer to the camera. In other words, the camera is the last position in the loop. But what if the camera is in the middle of the terrain? So what we can do is make two loops, one starting from one side of the terrain and one starting from the other side of the terrain, and both looping toward our camera's position. In both cases, the camera's position will be the final position. So I'll make a variable to hold that. I'll call it end x. Then let's also do it for the z-axis, so end z. Before we loop, let's find these values. Starting with the x. Well, if our camera x is less than 0, then, well, we always want to be moving toward the camera, so our end x will be 0. Now, if camera x is greater than grid size minus 1, we'll want to go in the opposite direction, again toward the camera, so set end x to grid size minus 1. If it's somewhere in the middle, meaning it is somewhere over the terrain, we'll set end x simply to camera x. We can do the same thing for camera z, replacing all the camera x's with camera z's, and all the end x's with end z's. And then now, around our repeat loop, we'll start with the outer z repeat loop. I'm going to repeat twice, right? Because we're repeating in two different directions. And we need to hold what direction we're repeating in for each of those times, which I'll call loop dir z. And then again, we should make one for our x, loop dir x. So before we loop, we'll set loop dir z to 1, and then at the end of that repeat loop, we'll set loop dir z to -1. So the first time we loop, it's 1, and the second time we loop, it's -1. Then, rather than setting z to grid size minus 1, we'll get an if-else. If loop dir z is equal to 1, we will set z to grid size minus 1. But if it's equal to -1 in the else, we'll set z to 0. And then we're going to stick that right at the top of our repeat 2. And now the amount that we're repeating by changes also. We're going to be repeating by the difference between our z variable and our end z variable. So the amount that we need to change our z to get to the end z. Then we always want this to be positive, so we're going to take the absolute value of this, then stick it inside our repeat loop. Then inside that loop, we change z by 0 minus loop dir z. Alright, now for the inner loop, we're going to basically do the same thing we did in the outer loop. We'll get a repeat loop around this, a repeat 2. Make sure that change z stays out of that repeat 2. At the top of this loop, we set loop dir x to 1, and then at the bottom of this loop, we set it to -1, just like we did with our z loop. And then, similar to what we did with our z loop, loop dir x equals 1, set x, the else set x, and then change x by 0 minus loop dir x instead. And again, for the input to this innermost repeat loop, we'll do what we did up here, where we have an abs of x, this time, minus end x. So again, just repeating basically exactly the same thing we did on the outer loop for the inner loop. Let us run this and see what happens. Well, for now it's looking pretty good, except we do have a stripe in the middle of our terrain. But if you think about it, that makes sense. That's actually a good sign that we have that there. Now if we go around this side, we should not see any more of those weird layering issues. If we go around to this side again, those layering issues seem to be gone. Now let's address this stripe a little bit. We can't fix it completely, but we can improve it by simply adding 1 to the inputs to these repeat loops. The abs of z minus nz plus 1 and the abs of x minus int x plus 1. If we try that out, yeah, there we go. That stripe is still barely visible, but less noticeable than it was before. Let's go ahead and add water in the valleys. Now our water is going to have a height of 0. So let's get an if else, and we're inside draw terrain in the innermost loop where we set our transformed positions. So we'll check if height is greater than 0. All we need to change is this very topmost transform position block. We'll put that in the if, and then duplicate it for the else and just stick this right here. Now the one in the else, where we have our height times detail, we're just going to replace that with a 0, because the height of our water is just going to be plain old 0. Now if we run this, the water will not be blue, but it will be flat. Now let's make the water blue. In draw point, we'll grab an if else, check if height is greater than 0, then if so, we'll set our pen to our green color, otherwise we'll set it to the blue color. And just choose a nice blue color here, like so. Then I'll put the pen brightness only when our height is greater than 0. So now we've got some lovely blue water. That's pretty bright. Maybe I'll adjust that color a little bit to be nicer. Yeah, there we go. That's a little better. So now we've got water and land. It's pretty shallow water. Under the water is a whole bunch of nothing. You can fly around down here actually, and it's kind of fun. Now you will notice that on the edge of our water, the terrain sometimes looks a little bit spiky. Now that happens just because of the order we draw things in. There's not too much we can do to fix this, but we can make it slightly less spiky by checking if height is less than, like say 0.02 when height is greater than 0. And then I'm going to move the pen size into the else of this. Then in the if, I'll set pen size to a smaller number like 500 divided by z. And then also in the water, I'll set pen size to that same amount. Now when we run this, you can see that at our borders, there's more, slightly less spiky. Like it's not perfect, but it's a little bit better. But you know, I still think it looks pretty good. And yeah, I mean, we've got 3D terrain and we can move around it, you know. The resolution isn't amazing, especially up close like this. It's, you know, from a distance I think it looks pretty good. Great job everyone for getting this far, and that about wraps it up for this episode. We have made ourselves some 3D terrain. As with my other tutorials, I'm going to share a Scratch Studio, which you can put your projects in if you wish to share them. Please do, I'd love to see them, and there will be a link to that studio in the description. Now there will be another episode of this. However, it won't be a continuation from this project. It will be a continuation from what we made in episode 1. And in that video, we'll be covering seeds, layered noise, and the possibility for infinite worlds. Then in the video after that, I'm going to combine that project with my 3D Minecraft tutorial. Now recently I've been uploading every week, but going forward, I'm going to have to tone that down to a video every 2 weeks or so. My uploading won't be quite as consistent. Hopefully you don't mind. Anyway, with all that said, I hope you enjoyed the tutorial. Have a great rest of your day, and goodbye!